2.3, linear programming, the simplex method, slack variables, and the pivot. We've been talking about optimization and optimizing, and optimize means you're going to find the maximum or the minimum value. But the problem is, if there are more than two variables, graphing becomes very difficult. The simplex method is a way to optimize problems that can't be solved using the method of corners. Think about it. What we've been doing in the previous sections, we'd graph some two-dimensional feasible region, and then we just found the corners, and the maximum or the minimum was going to be one of those corners of the feasible region. Okay, but as soon as we go to three variables, we're graphing in 3 dimensions. And so you're going to have some three-dimensional figure. Now you could still, I guess, theoretically find the corners of that three-dimensional region and still do the same thing, but it's going to be really, really hard to graph something in 3 dimensions. So imagine having to draw a three-dimensional figure and then find those corners. It's going to be really hard, okay? So that's where the simplex method comes in. Standard maximum form. We're going to be finding only maximized problems today. A linear programming problem is in standard maximum form if the objective function is to be maximized, all variables are non-negative, all remaining constraints are stated in the form. That's just saying standard form. Okay, we want standard form. We don't want slope-intercept form or whatever kind of form. But essentially what this means is all of our variables are on the left side. All of the variables are on the left side. That's standard form. So we've got this idea of a slack variable. Slack variable is a non-negative variable. I'm going to abbreviate that. That turns an inequality into an equation. It's kind of a weird concept, but we don't really want the inequalities. We don't want the inequalities. Look at problem 1, see all those inequalities, less than or equal 150, less than or equal 200. We don't really want inequalities for this process, so we're going to have to change them into equations, and that's where the slack variable comes in. So if you think about, let's think about a simple inequality. All right, so if I said x plus y is less than or equal 10. All right, think about some solutions to that. If I had solutions of that, let me say x, let's make an xy table here. If x was 1 and y was 4, okay? 1 plus 4 is less than or equal 10, okay, sure. 2 and 7. 2 plus 7 is less than or equal 10, okay, fine. What about like 5 and 5, all right? 5 plus 5 is less than or equal 10, okay. All of those are solutions. You could think of a million more if you wanted to, including fractions and decimals or whatever. But what we're going to do is we're going to insert a slack variable. Slack starts with S. We're going to insert a slack variable into that inequality. So we're going to say x plus y plus s equals 10. And so all we're going to do is put this slack variable into that and make it an equals. We don't want an inequality, we want an equals. So if you think about this table, 1 plus 4 plus 5 equals 10. And 2 plus 7 plus 1 equals 10. And 5 plus 5 plus 0 equals 10. All right, so all we did was we put some variable in there, some non-negative, that's going to be important, some non-negative variable that turns it into an equation. Number 1, restate the problem by introducing slack variables. Okay, so all we want to do is we want to take the main inequalities, okay, the main ones, and we want to put in a slack variable. Now, you've got 3 inequalities, and we can't have the same variable for each inequality. It's going to have to be a different one. All right, so we're just going to call it slack 1, slack 2, and slack 3. That's subscript. And I know people get confused when they see x1, x2, x3 because it looks like a mess, but that's basically like saying xyz. It's a better way than saying xyz because what's after z? What if you have 4 variables? What if you have 5 variables? This way you could go x1, x2, x3, x4, x5. And we could just keep listing, and you could have as many variables as you want. You don't have to worry about the alphabet or picking a new letter or whatever. So don't get confused by all the subscripts. That just means there's an extra one. Okay, so we want to restate the problem. So what we're going to do is copy this down, and literally all we're doing is changing them all into equations. So we've got maximize z equals 3x1 plus 2x2 plus x3 subject to, just copy 2x1 plus x2 plus x3, but we're going to insert a slack variable to make it an equation, equals 150. That's all we're doing. That's all we're doing. Add that, add that slack variable in there. So the next one says 2x1 plus 2x2 plus 8x3 plus s2 equals 200. And then the third one says 2x1 plus 3x2 plus x3 plus s3 equals 320. And then you've got the last ones, x1, x2, x3. This is kind of just a shortcut. All 3 of those are greater than or equal 0. So I just kind of shortcut the process and was lazy. But that's restating the problem by introducing slack variables. Now the good news is we're going to be able to skip that step. We want to get to the next step, form the initial simplex tableau. The initial simplex tableau, remember when we were talking about standard form? We want standard form. So most of these things are written in standard form. Okay. Standard form, standard form, standard form, but this one is not standard form. Okay, remember standard form, if I said, let's just make it z equals x plus 2y. If I had to put that in standard form, I would subtract over and I would subtract over. And I would say negative x minus 2y plus z equals 0. We want all of our variables. We want all of our variables on the left side and our constant number on the right side. That's what we're looking for. And so you should be able to do this in your head because you're just going to subtract this over and you're going to subtract this over and you're going to subtract this over. Okay, you're going to subtract all 3 of those things over. Maybe I should have done it like this. Subtract this over, subtract this over, subtract this over, because we want them all in the same order. All right, so we want to list out our variables. And so what do we have? We have an x1, x2, x3. Give yourself a little bit of room. And then we introduced slack variables, s1, s2, s3. And there is one other variable. We don't really need this step. We're going to kind of ignore that step. But we've got one other variable, and a lot of times people overlook it, and it's the most important one. Z is the variable that we are maximizing. Okay, we are maximizing that one. So first of all, list out your variables across like that. And now what we're going to do is we're going to go through each of these new equations that we just made. All right, so look at the first one. The first one was 2x1, 1x2, 1x3, one S1. We don't see S2 or S3 or Z in it. And then remember when we did Gauss-Jordan, we did a vertical bar was the equal sign, 150. You're going to have some stuff that's a little bit similar to Gauss-Jordan, but not quite. So keep that in mind. Look at the second one. Get 2x1, 2x2, 8x3. We do not have an S1, we have an S2 this time. No S3 and no Z, and it equals 200. And then we look at the third one. 2x1, 3x2, 1x3. We do not have S1 or S2. We have an S3, but no Z, and it equals 320. Now, after you get all of the inequalities, I want you to draw an underline. Okay, so you end up having like this cross right here. What we have is really a matrix. Okay, we have a matrix like that. But there's going to be one more row underneath that underline. Okay, so leave room for one more row, and that's your objective function. That's your first one. Okay, but don't forget, we had to put it in standard form. So we took this and subtracted over, and that's now going to make -3. -3x1. And we took this one and we subtracted it over, and that's going to make -2x2. And we took this one and we subtracted it over, and that's going to make -1x3. And we don't have any slack variables, and we don't need them because it wasn't an inequality. It was already an equation. Okay? Now, don't forget about the last variable. You already had this one Z on the left side. You moved everything out of the right side, and so it equals 0. Just like we did over here, we moved everything over to the left side, and we still equaled 0, or we equaled 0. So that is your initial simplex tableau. Okay, that's going to be important because basically what that represents is one of the corners of this region. So once we learn how to read the initial simplex tableau, we will be able to read one of the corners of this region. Okay. Now you don't know at this point if that's the maximum or not, but we'll see. Example 2. Set up the initial simplex tableau. So at this point, we don't even want to maximize. We just want to set up the problem. Okay. So this would be a good review of the last lesson when we had to do a bunch of story problems and stuff. Okay. Farmer has 100 acres of available land on which he wishes to plant a mixture of potatoes, corn, and cabbage. It cost him $300 to produce an acre of potatoes, $60 to produce an acre of corn, $180 to produce an acre of cabbage. He has a maximum of $20,000 to spend. There are taxes of $5, $10, and $15 per acre of potatoes, corn, and cabbage, respectively, and the farmer does not want to pay more than $900 in taxes. He makes a profit of $120 per acre of potatoes, $40 for corn, and $60 per acre of cabbage. So, it doesn't say maximize the problem, but that's what we would be doing. We would be maximizing profit. And I'm going to use P here instead of Z, just because I like to be descriptive. We're maximizing profit, and that helps me when I go through and I look at the numbers that are talking about profit. Okay, I'm going to call potatoes X, and corn I'm going to call that Y, and cabbage I'm going to call that Z. So you can use whatever variables you want. If there are 3 variables, I think X, Y, and Z makes sense. Unless, of course, you use Z for your objective function. If you use Z for your objective, then you don't want to use Z for one of your variables. But in this case, it doesn't really matter. So we've got 120x plus 40y plus 60z. And then we have to go through and find our constraints. Subject to. Okay, so 100 acres of available land. That means he could use up to 100 acres. He could use 90 or 75 or whatever, but he can't use 101. So something's going to be less than or equal 100. And so he's going to plant some mixture of potatoes, corn, and cabbage. That's a very common equation that you see. Add them all up, and that has to be less than or equal 100. It costs 300 for potatoes, 60 for corn, and 180, and he has a maximum of 20,000. Well, maximum, that's telling me less than or equal. So what do we have there? 300, 60, 180. There are taxes, so once you've seen a few of these, you start getting a feel for how they work. And he does not want to pay more than 900 in taxes, so that's another less than or equal. I know it says more than 900, but it says he does not want to pay more than 900. So it looks like that. And of course, all of your variables, you don't want negative acres of corn or whatever, so we throw that in there. All right. But the problem says form the simplex tableau. And the simplex tableau is going to be a matrix, and we're going to get rid of all the variables. So what you'll want to do is list out all the variables. So we have X, Y, Z, but we're going to have slack. Okay. So the first one is going to be S1, and the second one's going to have an S2, and the third one's going to have an S3. So we're going to have S1, S2, S3. And then way over on the right, we've got one more variable. Don't forget about the P variable here, P. All right, I see 7 variables in this problem, and I can ignore that statement. But look at your inequalities. The first inequality here says 1x, 1y, 1z, and 1s1. We don't have any of those 3 variables, and it equals 100. Look at the second one. Hopefully I have enough room here. 300x, 60y, 180z. Don't have S1, but we do have S2. None of these, and it equals 20,000. Third one, got 5x, 10y, 15z. None of these, but yes, there's an S3. There's no P in that equation, and it equals 900. Underline. And now we need to go back and grab the objective function. Okay, now don't forget, a lot of students really struggle with this. Okay, I need to have this in standard form. All right, think about where this equal sign is. This is your equal sign. So the only thing to the right of the equal sign is your plain number. All your variables have to be on the left side. So that's why you subtract this over, and you're going to have negative 120 for the x. And you subtract this one over, and you're going to have negative 40 for the y, and you subtract this one over, and you're going to have negative 60 for the z. It's already an equation, so you don't need a slack variable. And then, oh yeah, don't forget about the p. You've got 1p in this equation. And so think about it. We moved all of this out of there. It's going to equal 0. And so that's going to happen pretty much every time. We've made a matrix, and that's called the initial simplex tableau. Now, what's cool about this is, again, that represents one of the corners of this region. And so when we can read this simplex tableau, we can figure out one of the corners of that 3-dimensional region. Or, imagine if there's more than 3 dimensions. If it's 4 dimensions, I don't even know how to draw that, but we could find one of the corners of that region. So what's a basic variable? All right, a basic variable is, I'm going to write it like this. Oh my gosh, I can't write. Any column containing only one non-zero number. Find its value similar to the Gauss-Jordan method. All right, that's the basic variables. Okay, so basic variables, we find a column containing only one zero. So like this one would be basic because it only has one non-zero number. And so does this one, and so does this one, and so does this one. Okay, the other three in this case are non-basic. All right, so what's a non-basic? All right, non-basic are, columns with more than one non-zero. All right, any column with more than one non-zero number is going to be a non-basic variable. Okay, its value equals 0. All right, so we can calculate the values of those variables using this method. Okay, basic feasible solution is the solution. Now, it doesn't mean it's the best. Maybe not optimal. Meaning maybe it's not the maximum, but you can find one of the solutions, or in other words, one of the corners. Okay. So the non-basic variables for this table, we can see that x, y, and z all equal 0. X equals 0, y equals 0, and z equals 0 because they're non-basics. Now the basic variables, all right, pay attention, here we go, okay? It says you find the value similar to Gauss-Jordan. So what you're looking at is this 1, and you kind of think about as like 1x equals 100 or 1s1 equals 100. And so I can see right now that s1 equals 100, okay? You can probably figure out what s2, s3, and p are, but that's what the next problem is about anyway. So I don't want to confuse you. Number 3 says, read a solution from the following simplex tableau. Read a solution from the following simplex tableau. Okay, so we should be able to see which ones are basics. Basic variables have only one non-zero number. The other 3 are non-basic. Okay. Non-basic, non-basic, non-basic. All right. So again, think about it. The basic variable, you find its value similar to Gauss-Jordan method. Non-basic, value 0. So if I look at my non-basics first, you can see that x1, let's see, x1, x2, x3, you got s1, s2. You only have 2 slack variables, and you have a z. I've got 6 variables, and I can find the values of each of them. Okay. x1 is non-basic, its value is 0. x3 is non-basic, and its value of 0. s1 is non-basic, its value is 0. But the basic ones you're going to have to do like Gauss-Jordan. Okay, so look at this basic one, and you look at the only non-zero number right there, and that forces you to look at this number right here. Okay, and so its value is going to equal 45 over 5. And once you know what you're doing, you're going to be able to do this in your head. So I can see the x2 value is 9. 45 over 5. That's just how we did it in Gauss-Jordan. Same thing. You'd look at that number. So when I look at S2, I'm looking at this number, and that forces me to look at this number. So S2, the value is going to be 17 over 2. And you can reduce that if you want. Well, I guess you can't reduce it, but you could change it to a decimal if you want. And so then the Z value, you have to look at this 3, which makes you look at this 90. So that value is going to be 90 over 3, which is 30. What we've just found is one of the corners of that three-dimensional figure. All right. Now, one of the ways you're going to be able to tell that it's not the maximum value is when you look at this row and you see negative numbers, it's not optimal. Okay. This is a solution, but I can tell it's not optimal. Now we're going to work on a pivot. Let's look at example 4. Pivot about the indicated 6 of the following simplex tableau. So if you can't tell on your sheet, I tried to highlight this 6 right there. Okay, so circle it, identify that 6 right there. All right, so think about Gauss-Jordan. When we tried to pivot, we were trying to knock out everything else in that column. So that's exactly what we're going to do. We're going to knock out the 5, 6, and negative 50 using that 6. Okay, so what you're looking at right here with the simplex tableau is basically one of these corners. It's one of the corner points of that three-dimensional region or whatever. And we can look at the variables. We can read a solution. But what's going to happen is when you see negatives in this bottom row, you know it's not the optimal solution. I can see non-basic. Remember, a non-basic variable has more than one non-zero number. This is non-basic. This is non-basic. And when it only has one non-zero number, it's a basic variable. So all of these look like basics. Okay, but I can read a value, and non-basic variables have a value of 0. So I can see x1 is 0, x2 is 0, x3 is 0. That's not very interesting. And I don't really care. I don't really care about the slack variables at this point, but if you look at the Z value, that's what we're trying to maximize in this problem. And that's where we said, like, look at Gauss-Jordan, this 1, make sure look at this 0. And if you know what you're doing, you can tell that Z equals 0 in this problem. And so it should be fairly obvious that that's not going to be optimal. That's not going to be your maximum value. If you look at this shaded region, you know, that's one of the corners. That's one of the corners of the shaded region, but it just so happens that it's not the optimal solution for the problem. So we have to do this thing called the pivot. And the pivot is going to involve knocking out these numbers. All right, so what you want to do is copy down the table. And if you notice, you've got, hopefully I can have enough room here, x1, x2, x3, s1, s2, s3, and z. And then you need to leave a little bit of room on the right side for your constant number. But we're going to set up this table, and the circled row can stay the same. So you've got 3x1, 6x2, 2, 1, 0, 0, 0. And remember, the vertical bar means equals 60. So what we have to do with the pivot is we have to knock out this number using the 6. And so think about Gauss-Jordan. When we used rule, we have to knock out a 5 using a 6. It's a common multiple. You're going to do 30 minus 30. So I think we should do 6 row 2s minus 5 row 1s. That's going to be 30 minus 30, and that's going to give me 0 where I want it. All right, so we have to use that rule all the way across this row. So we start with the 8. Okay, and we want to do 6 of the 8s minus 5 of the 3s. That's 6 row 2 values minus 5 row 1. That gives me 33 for my first number right here, 33. Okay, keep going. 6 of these is 30 minus 5 of these is 30. 30 minus 30 is 0. That's exactly what we wanted. Okay. If you can do it in your head, do it in your head. 6 of these is 24 minus 5 of these is 10. 24 minus 10 is 14. If you can't do that in your head, use a calculator. You've got 6 of the 4s minus 5 of the 2s. That's going to be 24 minus 14. Or 24 minus 10 is 14. Okay. With the zeros, it gets easier because you're doing 6 zeros minus 5 1s. That's 0 minus 5 is negative 5. And 6 of these minus 5 of these, that's going to be 6. And 6 of these minus 5 of these is going to be 0. 6 of these minus 5 of these is going to be 0. 6 of these minus 5 of these, that's going to be 480 minus 300 is 180. Use a calculator if you need to. I know that's 180. Okay. Next, we have to knock out this 6 using the circled pivot element 6. I think all we have to do here is subtract row 3 minus row 1. Just subtract the values. So 3 minus 3 is 0. 6 minus 6 is 0. 7 minus 2 is 5. 0 minus 1 is negative 1. And where am I? S2. 0 minus 0 is 0. 1 minus 0 is 1. 0 minus 0 is 0. 120 minus 60 is 60. Don't forget your underline. And then we go to the bottom and we've got to do the same thing. We have to do the exact same thing. So let's look at this negative 50 using the 6. A lot of the times with big numbers, you just multiply them. So if I took 6 of the row 4 numbers and added 50 of those row 1 numbers, that's going to do it because 6 of the negative 50s is negative 300 and 50 of the 6s is positive 300. That's going to knock each other out. That's going to cancel out. All right. But we're using this rule all the way across this bottom row. So again, if you need to pull out a calculator, do it. You've got 6 of the negative 30s plus 50 of the 3s gives me negative 30. And the next one, 6 of these plus 50 of these is going to be 0. And the next one, 6 times negative 15 plus 50 times 2 is 10. And then again, the zeros are kind of easy. 6 zeros plus 50 ones, that's going to be 50. And 6 zeros plus 50 zeros, 0. 6 zeros plus 50 zeros, 0. 6 ones plus 50 zeros is going to be 6. And 6 zeros plus 50 of the 60s, 50 times 60 is 3,000. Last thing I would do here is make sure you box in your matrix here. Okay, so that's what your new Simplex tableau looks like. That's not initial, that's not the starting one, that's the next one. Okay, and what we've just done is we've produced another one of the corners of whatever this region looks like. All right, so it's another corner. And again, when you know what you're doing, you're going to be really disappointed when you see this negative number because that means we don't have the optimal solution. All right, so again, you can kind of see that this is non-basic. This one's basic, non-basic. Remember, a non-basic has more than one non-zero number. This one's non-basic, basic, basic, and basic. So your basic variables have one non-zero number in that column. So we can read a solution again. It's just we know that it's not going to be the optimal solution. Got x1, x2, x3, s1, s2, s3, and z. Okay, so the non-basic variables all have a value of 0. So I can see x1 is non-basic and x3 is non-basic and S1 is non-basic. So all the non-basic variables have a value of 0. But for the basic variables, you can find the values similar to Gauss-Jordan. So if you think about it, there's only one number in X2. There's only one number, only one non-zero number. And that 6, if we were doing Gauss-Jordan, we would be looking across at this 60. And so for X2, it's like it says 6x2 equals 60. And we don't have to write this down, but we're kind of looking at it like this. And you divide both sides by 6, and your value is going to end up being 60 over 6, which is 10. So X2, the value is 10. Now, I want you to do that in your head as soon as you can figure out what to look at. I know sometimes students' eyes go cross. There's so many numbers. But when I look at S2, there's only one number to look at. It's got to be that 6. And look straight across at that 180. We're doing 180 over 6, which is 30. That's the value of that slack variable. And for S3, there's only one number to look at. Look at the one that's not 0. Look straight across at that number. We've got 60 over 1 is 60. That's the value of that variable. Now for the Z value, again, it's basic, so there's only one number to look at, 6. You're looking at 3,000. So 3,000 over 6 is 500. That's your value. That's your Z value. Now again, when we see this negative number, we know it's not optimal. We just know it's one of the corners. It's one of the corner points which produces that value. We'll have to figure out how to find the optimal solution in the next lesson.